Alrighty. So today we'll go ahead and get started, and we'll be talking about linear regressions. So basics of linear regression today. All right. So the first thing we'll do here, I'm going to draw a hypothetical graph with some data points. And these are just going to be sort of generic X's and Y's. And so you may have a whole bunch of data points that might look something like this. And the whole idea of regression, which is essentially what we're going to be focusing on for the majority of the class, is to model the relationship between variables. So here, what I'm going to do is I'll go ahead and maybe draw a line through these points. Might look something like this. You might have something that looks like this, or like this. Or we could even draw a line that maybe goes like that. And so the kind of question that we are trying to get at, and sort of most simply in the linear regression, right? So which line is best? And I'll put sort of quotes around it, because best is going to be sort of a subjective measure in some ways. And so why are we going to be calling it the best? And I say that it's subjective because you come up with a particular criteria for deciding what is quote unquote best, which in turn, that criteria itself can then be an objective measure of it. But at the end of the day, you could, in theory, use slightly different metrics to come up with arguably different sets of criteria for choosing one particular line over another. Okay, and so in most of the way that folks traditionally do linear regression is to use a particular measure for linear fit. And so this is known as ordinary least squares regression. And this allows us to then have an objective measure of linear fit. And so if I go back to this chart above, let's delete a couple of these lines for clarity. And let me get rid of this. So the way that ordinary least squares works is that I can look at the distance from each of these points, right, to this line. And I can measure that distance in order to figure out, you know, if I draw the line in a certain way. Okay, so let's say these are all sort of red dotted lines here. And if I had, for example, a blue line like this, you could argue that the distances from my data points to my line are going to be a lot bigger. And so essentially what you're going to be doing is trying to minimize the distance. And actually in ordinary least squares, also known as OLS, you are not only minimizing the distance, so in OLS, minimize the squared distance. Okay, and so why is it that we minimize the square distance as opposed to just the regular distance? It actually has to do with the fact that in some cases you're going to have a positive difference, and in some cases you're going to have a negative distance. So if you don't square them, then these terms can actually cancel each other out, and you can get some bias depending on if you've got lots of points above or below the line. And so by squaring it, you're basically saying I care equally about points being above the line and being below the line. One of the artifacts of squaring them, however, is that if I have, say, an outlier that's really far away, right, this distance is going to be much more impactful than points that are closer because the distance gets squared. So that is one sort of thing to keep in mind. It doesn't end up being really all that relevant all of the time, or a lot of the time. So let's see. Okay, it is possible. It is actually possible to, instead of doing the square of those values, to actually take the absolute value. But actually, the reason why it's done as a square as opposed to the absolute value actually has to do with computational reasons. And before we had, computers that could solve these numerically very easily for us, the analytical solutions for these types of problems was a lot easier to do with the square as opposed to doing the absolute values. So that's one sort of reason why you don't see absolute values very commonly. Okay, let me make a new sheet here. We'll go ahead and draw this again. So the actual equation of this particular fit to the data, which is just a line, can be defined with two parameters. Okay, so you have your slope and you have your intercept. So hopefully everyone remembers this from algebra, but the general form of these we used to write as ax plus b. At least that's what we did in my high school. And in linear regression, it's essentially the same thing, but those parameters or coefficients are typically labeled as betas. So we'll call this beta and alpha. Sometimes you'll see it could be beta 1 x plus beta 0, but these are all effectively the same thing. And so this is your beta coefficient. And this describes the slope. And this coefficient describes your intercept. Okay. Very quickly, I also want to mention that when we were talking about these values here, this is known as your error term, right? It's the difference between what you're predicting, okay? And when I say what you're predicting, that is the fit that's going through all these points. So your prediction is the red line. So this is your prediction. And so this term here is the error term. And this is also known as a residual. All right. So when you take like an econometric class or statistics class in regression, they will sort of teach you how to solve for your betas by hand, right? And you can kind of figure out where these betas will come from. And so we're actually not going to get into that. And in fact, it'll be kind of a sort of a black box, because when you run a regression, a linear regression in R, it kind of just does it for you automatically. But I will sort of talk a little bit more about the application of calculating coefficients, and we'll get into this, some of this in practice when we go through the code that will do some of this. But there are, in reality, sort of two approaches that are commonly used to essentially calculate your betas. And so this is numerical methods versus analytical methods. And so this kind of applies to optimizations generally. So you can sort of quote unquote solve it by hand, where you have a real sort of exact solution for a particular optimization problem, or numerical methods where you use some kind of algorithm to approximate the solution. Because linear regression is such a common class essentially of optimization, right? And it is an optimization because what are we doing? We are minimizing an error, right? And anytime you're doing a minimization problem or a maximization problem, it's essentially some form of an optimization. So this is actually a solved optimization. And you may have seen this equation before. Again, this isn't something that you'll have to sort of memorize for this class, but if you've taken any class in regression or econometrics, then hopefully this will be familiar to you. So this is the essentially solution for solving your betas. If you take a matrix of your x's, right, you can transpose it, multiply it by x, and then invert the matrix. And then you multiply it by x transpose times your vector of your y's. Okay, and so when we do our operations in R, this is what is happening behind the scenes. And the way this works is they have this, it's called a sweep operator that does the matrix inversion. And the sort of main reason I'm telling you this is that this operation, a matrix inversion, is actually a memory intensive operation. And that tends not to be really a big issue for most people doing data analysis at sort of smaller scales. But it turns out that when you are doing really big data analysis, and I'm talking about, on the order of gigabytes, where you are, really saturating, for example, the amount of memory on your computer, this can actually be kind of problematic because solving the matrix inverse, again, is from a big O perspective on the memory side, is a squared operation. And so the way that actually some machine learning algorithms will approach this is to actually go back to a numerical method. And so it is not uncommon to see gradient descent methods be applied to regressions, linear regressions, when you're using really, really big data sets. And so the way this works is you solve for beta iteratively by, I'm just going to say quote unquote, guessing and checking. Okay, that's not entirely an accurate description of gradient descent, but it's not actually something that we're going to get into. But if you ever do run into issues with memory limitations as it pertains to solving a linear regression, just go back here, and I just want to point out that there are other methods for solving linear regressions that can be used. It's not going to be very common, but in case any of you do, just know that there are alternative methods. Okay. Oh, okay. I see that I actually skipped a question from earlier, which is whether or not the fits can be based on perpendicular distance rather than I guess the vertical difference in y. So I guess what that would mean would be something like this, as opposed to going up and down. So, okay, the answer to that is kind of. It would be a different type of metric. It would actually be a very different type of metric from the way it's traditionally done. And this gets to where I was kind of saying, quote unquote best, right? And the main, there's a couple reasons why this isn't done, but probably the biggest one is that the calculation of the perpendicular distance is a lot more complicated than doing the vertical distance to solve, especially by hand, which is for practical purposes why a lot of these decisions were made, back 40, 50 years ago. So yeah, I'll kind of leave it at that. It's similar to the absolute value thing. Solving the problem is slightly harder without computation. But actually, if it's something, if that's something that's is of particular interest, you can look into this, or you could even write your own algorithm and see how it compares to linear regression. I suspect there's so much less support in doing that sort of thing that a lot of the methods that you could derive are probably going to be a lot less efficient than the ones in your traditional linear regressions. Okay, so let me jump over to RStudio. Okay, and hang on, I think I saw another question pop up. Yes, okay, so good question. So how do we determine whether or not we should use a linear regression or not for a certain data set? Okay, that is gonna be like a very thematic topic as we go throughout the course. And so we're kind of starting at the most basic, how to do a linear regression. And I would say about halfway through the course, we're going to start getting into other types of regression. And that's where we're really going to address this topic of, why and when it makes sense to do linear regression, or even sort of what are the implications of using linear regression versus other, say, semi-parametric or even non-parametric approaches. Yeah, and so I think I'm not going to answer that question sort of straight up right now, because that's going to tie into a whole bunch of topics sort of down the line. And hopefully it'll be something that will be at least one of the important considerations when you think about doing any sort of data analysis, whether it makes sense to be doing just a linear regression approach. Alrighty. So what we're going to do is we are going to generate some random data and then just perform some linear regressions. Okay, so this first line here, I am running a function called runif, which I believe is one that I've talked about before. But just to review, this runif stands for random uniform, which means I'm going to draw from a uniform distribution. The default values for the random distribution are between 0 and 1. And I'm asking essentially to draw 20 points. So if I run this and I look at my x, what I'm going to see is a vector of 20 values, of 20 random values between 0 and 1. Great. Okay, so here's my 20 values. So those are going to be my x's. And then I'm going to create another variable called deviation. And this is going to be very similar, except it's going to be, so I'm going to draw 20 points. We can see up here the arguments, so n, mean, and SD. So I'm going to leave the mean at 0, but I'm going to make a standard deviation of 0.1. Okay, and so this is going to give me 20 points, and they are going to be randomly distributed around 0 with a standard deviation of 0.1. Okay, and I am going to now create a set of y's. And actually, you know what? Why don't we actually call this, instead of deviation, I'm just going to call this random error. Okay, I think that's probably a better term than deviation. Okay. So hopefully we can see what's going on here. I've got my random error, and then I'm creating a relationship between my x's and y's. Okay, it is a linear relationship, right? My slope and some error terms. And so I can see what my y looks like. Okay, a bunch of numbers. Actually, probably the easiest thing that we can do. Yeah, so that's right. So this is just random error or noise. So I'm just going to show everyone what this looks like. Actually, don't worry about this. This is more kind of just to make the graph pretty, but we don't really need to do that. Let's run this and see what it looks like. Okay, so we've got our graph here. If we didn't have this random error term, all of these points would just be on that line. And in fact, you can see, we could see what that would look like if we did something like this, y equals x times 0.5. So it's identical to this, except we've got random noise associated with each of those points. Okay, and so we'll actually be doing this type of thing a lot. And the reason why I kind of like to do this and generate my own set of data is because this line 3 is what we know to be, right, because we defined it as the true relationship between my x and my y. And so whenever you're doing regressions, oftentimes you are attempting to figure out the relationship between your variables, in this case, your x's and your y's. And unfortunately, in the real world, you very rarely know the actual relationship. But in this case, because we do know the true relationship, we can always kind of reference back to it and see how well our regression is doing. Okay. So I'm going to create a model fit, and I'm going to use the function LM. So LM stands for linear model. And you can see in here, there's actually quite a few options that you can put in here, but we won't worry too much about that. What we'll do right now is simply to do my regression of y on x. So let me quickly say, just for nomenclature's sake, so I say y on x, which is you always say, oops, I accidentally cleared that. So y on x, which is your response variable on explanatory variable. Okay, and okay, the only reason why I bring this up is because this is how the nomenclature is used in reality, and this can be confusing. Actually, it was confusing to me when I was learning about this, and so on the homeworks, when I say something on something else, it's always your response variable on your explanatory variables. Okay, so we'll go ahead and run this, and we'll now have a model fit. And I can look at the results of my linear regression by hitting summary. So it looks something like this. And actually, I'm gonna rearrange this a little bit. We're gonna actually create a data frame here. And I'm doing this to show you something. All right, so if I look at this data frame, so this is my first table. It's just my 2 vectors put into a table. And the reason why I'm doing this is that when you are actually doing linear regression on data, the way that you would reference it is by doing this. And so here you can do regressions on columns from a table, as opposed to referencing the vectors directly. So usually you'll have all your data arranged in these tables. And so you can call the table and then write out the columns like this. So this will be the same thing. And we can see what this looks like by adding, or you can look at the fit of this particular model by adding this. And you can see the line being added here. And I can even change the color if I want. Okay. Great. All right, so we know that the true form of the relationship is 0.5. Okay, and so if I go here, and we also know that there's no intercept, right? We know that, so this is just the random noise term, but there's no actual intercept value between my x and my y. Okay, and so if we look here, we can see the estimates for the linear regression. So on my x, it has 0.0589, and here it's negative 0.066. Okay, and so this is kind of close to 0, but this is something like 20% off from the true value, right? And so that is what our linear model is attempting to get at. It's the true value, and we can see, right, that it doesn't quite match. But that's okay. You know, it so happens that it's a little bit off, but there are a whole bunch of other sort of diagnostics about the quality of this model being shown in the summary, which we can talk about. And so the next things to think about very commonly are standard errors, and then you may have heard of this value called an R squared. So let's have a look at sort of what those mean. Okay, so let's go back to our whiteboard. Unless there are any questions. Okay. So let's think about this standard error. So before I talk about the sort of qualitative interpretation, we can kind of go through the standard definition. So again, this is something that you would learn about in your regular statistics class. And so your equation of the standard error can be calculated like so, except, okay, and again, this isn't something that you'll need to memorize or anything, just kind of as your reference. So it's going to be the difference between your yi minus yi hat. Okay, and so this isn't something that I've talked about yet. So yi is equal to the actual value, and then yi hat is equal to your predicted value. So if I were to draw a whole bunch of points, actually, let me draw this in a particular way. So let's just say we have something like this. And our line. You might have a particular prediction if this is 0.1, and this is your 0.1 for your prediction, then yi hat would be this value here, and this is your actual value. So this is simply, so this term here is simply the error term. Yes, there is a square. I'm not quite there yet. I stopped writing in the middle of the equation to explain yi hat. But yes, there's a square there. N minus 2 divided by xi minus x squared. Okay, so this is not to be confused with a standard deviation. So standard deviation is data's deviation from the mean. And then standard error is how precise is our estimate of the mean. So I want you to consider let's say I have the exact same set of points, but they are dispersed just slightly farther away from each other. I'm kind of trying to copy the graph on the left, but I'm kind of spreading the x's out a little farther. But the line is still kind of in exactly the same. So you could have same beta values. So let's suppose hypothetically that I were to take a point away. How much does your beta change? And so hopefully you can see that the contribution of a sort of particular point and its influence depends on kind of the distance, right? And so as I, for example, take away points or add points into these two charts, you can imagine that the line, that my line can kind of wiggle or adjust to a greater extent when the points are sort of more influential, and then maybe less so if the points are less influential. So more if it looks more like on the left versus on the right. You can think about how sort of quote unquote influential the points are on sort of the slope of that line. And so the whole idea of the standard error is to think about how likely is it that my slope is actually zero, right? So is the data actually distributed in such a way that we can statistically and confidently say that that line isn't just kind of, oops, hang on, isn't simply flat like that. And so you can imagine that if I draw the data from a random distribution again and again, my line is going to look, it is not going to be having exactly the same slope, okay? And the metric that we commonly use is basically saying that, hey, if that slope is not equal to 0 10% of the time, you know, then we say say the slope is statistically significant with a p-value of 0.1. If we find that it is not flat or not 0 5% of the time or less, then we say that statistically significant with a p-value of 0.05. And so that is all that means, right? For a standard error, it is not an end-all be-all of the quality of a model, or even necessarily the quality of a coefficient, and we'll sort of talk about that a little bit later. I just sort of at this point want you guys to sort of take away that it is measuring sort of one particular thing, and that just because a variable is statistically significant, it doesn't mean anything beyond this idea that it's different from 0. Okay. Any questions about that? Okay, and we'll be sort of revisiting the interpretation of the standard error throughout the class, and so hopefully this is one of the fundamental things that'll be easy for you guys to really jump on and interpret. And yeah, and I'll sort of try and emphasize that point about, you know, exactly what the standard error means, and not to sort of put more value on it than its real interpretation. And the other metric that we'll talk about now, that is also very sort of commonly used as almost the catch-all for the quality of the model, is the R squared. So this is known as the coefficient of determination. And the question that this metric measures is essentially how much variation is captured by the model. Okay. So the actual equation for this is equal to 1 minus sum of squared residuals minus sum of squares total. So this is equal to 1 minus the sum of yi minus yi hat, right? Again, this is the error term squared divided by the sum of yi minus y mean squared. Okay. And I think the easiest way to kind of understand what this means is to look at a comparison chart of these two things. Okay, so I've got my x's and my y's. So we'll do something like this, and I'll try and replicate this over here. So this is y mean, and this is y hat. Okay. And the question here is how much variation does the fit capture compared to the average? And basically, the idea behind the R squared is to create a really simple standard of comparison. It's basically saying, okay, if I just take the average of my y, my values, and compare everything to that, does the fit that I'm creating actually do a better job than, and then essentially doing this really quote unquote dumb way of estimating my y's, right? And so the R squared is handy because you'll, by creating this ratio here, which is always essentially going to be between 1 and 0, you can very simply and sort of crudely create a standard metric across any set of models. But again, kind of similar in what I was saying with the standard errors, this is just one other metric that we can use to evaluate the quality of the model, and it is not kind of an end-all be-all. And in fact, if I were to go back to my example in R, and let's go ahead and do that right now. So I could, like, very easily, you can imagine, create an artificially small R squared value, right? I could just explode my standard deviation here, where my error terms are really, really large. And what that would do is essentially reduce reduce the R squared, because now your X's are more likely to be sort of farther from your fit line. But you could still get a coefficient that's really close to 0.5, right? And so I'm actually hypothesizing about this. I don't think I've actually tried this, but let's do that. So let's do something like SD of 10. So if I run all of this and my model fit, oh, I need to redo that. Yeah, so your R squared ends up being really small, but it would not be impossible for this value. In this case, it's not. I probably need to find a seed that does this, but for example, I could hypothetically get my values for my X coefficient to be really close to 0.5, but I could have a really terrible R squared, like something like 0.01 or smaller, right? And then if that's all you go by, and you just say, oh, the R squared is really small and therefore it's a bad model, we in fact know that the model could be really good, because we know the true value of our coefficient, which is 0.5, and in theory, your estimate could be really close. So that's one thing to keep in mind. Again, the R squared, it means one thing. It doesn't necessarily mean, it's not the only sort of metric of being able to evaluate how good the model is. What it does tell you in this particular example, though, right, is that the line itself, there's a lot more variation in the data compared to the points. In fact, let's go ahead and plot it. So this relationship could actually be a very real relationship. It's just that there's a whole bunch of random noise. And so yes, when I think about the actual meaning of the R squared, it is true that my line doesn't capture a lot of that variation. However, it doesn't mean that the line itself is not an accurate representation of the true relationship between my X and my Y. Okay. Let's quickly take a break for 5 minutes at this point. So we'll start again at 3:09. Yeah, and then please let me know if you have any questions about the material or the code or anything else, and I'll happy to chat.
So is it?
I have a quick question. Oh yes.
Oh, correct.
Yep, go ahead.
So is it possible that the near horizontal line we're seeing on the screen right now, that's because your X data set is based off of like it has to stay between 0 and 1, and then you added an error of a standard deviation of 10, I think you did on it.
Yeah,
So
yeah, exactly. And
that's kind of what skewed it over to be almost horizontal.
Well, yeah. Well, if you look at the x-axis, it goes from -20 to 20, whereas here it goes from 0.2 to 0.8. So that red line, we know that the true red line, or the true line, we know that the true line should be a slope of 0.5. And in this case, this slope is actually a little bit larger, it's 1.4. But I could come up with a data set that makes it close to 0.5, yeah. And then there's another question.
Yes. Actually, what's the difference between RMSE and R square when we use RMSE or when we use R
Yeah,
square?
yeah, I will talk about root mean squared error in a little bit. We're not going to get to that in this lecture, but root mean squared error is another metric that we're actually going to be using that a lot in this particular class. It is another metric for determining how well your model essentially predicts the data. So it's another metric for measuring the quality of a model, and it's actually one that I tend to prefer. It's really big in machine learning as a metric for validation, and yeah, and so among the sort of suite of things that we think about, it is something that I would, even though I personally kind of prefer that metric, it is even then, it's just another sort of tool in evaluating the model, and I think the most important thing is really understanding sort of what all of these metrics mean, so that you're not kind of like sort of overemphasizing the quality of your model based on just like one or two particular metrics. All right. Let's continue on. And actually this, I realize my example 2 is kind of getting to this other point that I was making. Let's take a quick look. So let's do the exact same thing, but let's increase the deviation. So I'm going to multiply by 2, and then I can quickly plot what that looks like. So the points are going to be scattered in exactly the same way, but they're going to be twice as far from my fit line. So here I'm going to make a new data table called for model 2, which is going to be the same thing, except it's now going to have my y2 values, which is my vector here, where the deviations are twice as large. And then my model is going to look like this. With data from for model.2 table. So I'll go ahead and run that. And let's just take a quick look at that. Okay. So let me see. So here we can see the estimates, again, very close to 0 and 0.62. And this is in comparison to the first model, which gave 0.43 and negative 0.03 for my intercept. Okay, so let's go back to thinking about the interpretation. Again, we know that the true value should be 0.5, and we're a little bit off. But in fact, one of the things that you'll notice is that, okay, there's this standard error value, and we were sort of talking about that in relation to the statistical significance. And so let's sort of recap some of the theory we were talking about from the whiteboard and think about how to interpret it here.
Alan, sorry, could I ask a quick question?
Yeah, absolutely.
In line 15, you've written deviation times 2.
Yes.
Did we redefine deviation? I thought we just renamed it as like random error.
Oh, you're right. Oh, sorry. Yes. Thank you. I totally forgot that. Okay, so let's try that. So it might be a little different. Okay, so in fact, this time our estimate is 0.37. So a little bit different. Yes, thank you. Okay, and so we'll get to that comparison in a second. I want to jump back to our first model. Okay, it has a standard error of 0.09. And so this is describing essentially our estimate, our prediction of the mean value of our fit line, right? And so the mean value is 0.43, but it's got this standard error. And so the way that you interpreted it is that you know that it is normally distributed with this sort of standard error. And so if I were to go sort of on both sides, I would know that sort of 95% of the possible slopes, right, my estimates here are within 2 times the standard error. So that would be, you know, it would be, let's see, 0.43 and 0.09, right? So 0.43 minus 0.09 times 2, and 0.43 minus or plus 0.09 times 2. This means that I know that 95% of the times, right, that my slope should be between 0.25 and 0.61. Okay. And so when you hear about a coefficient being statistically significant, that just means that you know, less than 10% or 5% or 1% of the time, in this case, right, the 3 stars is referring to 0.001. So less than 0.1% of the time is the slope of that line 0. And so we are we have demonstrated that there is statistical significance, or there is a statistically significant difference from that slope being equal to 0. What does that tell you? What does this tell you about how realistic our estimate is compared to the true value? Can anyone? Right, okay, so the statistical significance, right, doesn't tell you anything about that. This only tells you how different it is from 0. It doesn't tell you anything about how close this is to the true value, because in reality, you'll never know the true value. And so sort of, again, keep that in mind. The intercept, which we know the true value is also 0. In this case, it says, well, 60% of the time, your intercept is going to be 0 or greater in this case, because it's starting out negative. So in this case, it's saying, oh, it's not likely that it's necessarily different from 0. When we jump over to our second example, we can see that the estimate is actually a little bit worse, but your standard error is also larger, right? And so in this case, 95% of the time, then we're saying what, 0.3691 minus 0.18 times 2, and then same thing plus. So 95% of the time, the slope is going to be between 0.0091 and 0.7291. So it's actually pretty close at the sort of 5% level. So you only have this sort of one level of statistical significance. Okay, and then the other thing is you have your R squared value here. So 0.1883. And that is saying that, again, about, say, 18%, right? Or it's capturing this proportional value of the variation in the data. And as we were sort of noting before, as you increase your standard error, your R, or not your standard error, sorry, your random error, your R squared is going to decrease. So when I look at my second example, it has an R squared of 0.188 compared to my first one, which has an R squared of 0.56. Okay, great. Any questions about that? Okay, let's do a slightly different example. So this time I'm going to draw 1,000,000 points. And let's do something like this. Oops. It's going to be between 0 and 50 instead of between 0 and 1. We're going to have a new random error, which is going to be 1,000,000 random errors with a mean at 0 still, standard deviation of 5. And then we'll do something like this. Y3 is x3 times 0.5 plus my random error. And let's plot this to see what it looks like. Hopefully it doesn't crash because I'm plotting 1,000,000 points. while that's going on, I'm gonna kind of do the same thing here. I'm just gonna make this table. And we'll run a linear regression on this. And you can see it's taking a lot longer when you run a regression on a million points. This might be getting, so back to the point about numerical methods versus analytical methods. This might be getting to the point where you might consider doing like a gradient descent type of approach, which would solve much faster in this particular example because of the size. And the plot is not actually showing up. I don't know if it crashed. But that's okay. You can imagine it's just kind of a similar as this, except we have a million points instead of, oh, there we go. Oh, that was, and sorry, I misspoke. I guess it was still plotting, so that wasn't. So that it still runs very quickly with a million points. So let's take a look at this one. Okay, and so we've added sort of a whole lot more data. And even though you've got all of this noise, right, we can see all of the crazy amount of noise that's happening from my random error term. It actually does a really, really good job at being able to differentiate the trend that it sees compared to all of the noise and random error term, right, in our data. And we can see that when we fit it to a million points, it is really, really close to the true value, right? We are fortunate in being able to know that the true value in this case, which is 0.5, and so you can see how close that estimate is. And in this case, this R squared value is 0.67. And I think that is not so different from our very first one. So let me scroll up really quick. Yeah, it's 0.56. So it's a little bit higher, right? But it can be difficult to really sort of convey necessarily just from an R squared, how much better that this model might be compared to our first example. So again, context matters when thinking about a lot of these metrics that talk about the quality of the model. All right. And I want to kind of emphasize these points that I've been making by showing you guys a really famous set of data points. And so I'm gonna load in this data, and then I would like for some folks to maybe volunteer to help me interpret these models. Okay, so this is data from that's known as the Anscombe Quartet. So I'm just going to, okay, hang on 1 second. Yep, wrong place. Okay. Okay, so let's try that again. So I know at this point you guys aren't going to be able to follow along because I haven't posted the Anscombe Quartet data yet, and that's kind of on purpose. So you can just kind of follow along here. And so, okay, I would like for a volunteer to help me here, and maybe just walk through this data and give me your interpretation or your opinion of this model. So who wants to volunteer themselves? Anyone?
Sure, I'll do it.
Yes, great. Thank you. Yeah, so I've pulled up the regression results right over here, and so maybe look at some of the things that we've talked about and tell me a bit about it, and maybe tell me what you think about this model overall.
Sure. So the intercept is statistically significant at the 5% level, and so is X1. X1 is quite significant, like it's significantly different than 0.
Yep.
And it's an upward sloping line, like it's got a slope of 0.5 and an intercept of. And then the R square is, I guess that's decent. It's not too bad.
Yeah. Okay. So and I am kind of this is kind of a trick question, but I'll kind of just ask you, like, what do you think of the model overall? You think it's a fairly decent model? It's not very good? Like, how would you, if for example you saw this in a paper in a presentation, like what would you think about this?
I would think the R square is kind of low, but like the good is that the variables are significant, so they're important. Yeah.
Okay.
But it doesn't really explain, like, I think there's a lot of probably white noise in the data points.
Sure.
Like,
okay.
Yeah, it has a lot of variation. So the systematic part of this is on the lower side, you could say.
Sure. Okay, great. And actually, I do want to bring up this other point that you said, where you felt that the R squared is low. So actually, that's kind of interesting, because you do tend to find that depending on the discipline that you're in, if you're in sort of like engineering or economics, or if you're in statistics or that sort of thing, the quality of the R squared can actually be pretty subjective across fields. And so what like a social scientist might think is really high, you might find that a statistician would say, oh, that's really low. And so that's a sort of further thing about the interpretation. And I only bring that up because you said 0.67 is kind of low, and I think in a lot of the work that happens in my field, I would actually say that's actually kind of high, and that has nothing to do necessarily with anything directly about the model, right? It is our sort of subjective opinion about how good that metric is. So okay, great. Thank you. So that's the first model, and I would like a different volunteer to help me summarize model 2. Okay, so thank you, Maha. So someone else help me out here. Anyone? Your job is going to be easier.
We can't see the model results yet.
Yeah, I haven't hit enter on purpose. You have to agree before I hit enter.
Okay, I'll do it.
You'll do it. All right, perfect, great. Okay, so this is a different data set, and I would like for you to help me interpret these results.
The R squared seems similar to what
Yeah.
we saw from the first time.
Is that the only thing that looks similar?
No, the x2 and I think the intercept is similar too.
Yeah. So just as
with
a
actually
comparison.
with actually similar levels of significance.
Yeah, great.
So from looking at it, you can't actually tell that they're different data sets unless you
great.
tell me that. Yeah.
Okay, so it's likely that you would have a similar opinion of this model. And I won't ask for volunteers for models 3 and 4 because you can probably imagine what I'm going to show you here. Here's the results from model 3. R squared about 0.67, intercept 3, x3 coefficient 0.5, and let's do model 4. Okay, also very similar, 0.667, intercept 3, x4 is about 0.5. Cool. Now let's take a look at the data. Before I show you this, the main thing again I want to take away is that, like, when you read papers or when you go to like a presentation or like a conference and you see someone pull up this table of values for their statistical significance and for the R squared, like, know that all of those metrics, again, that we very often use as kind of measures to determine the quality of a model, like, are telling you very specific things, and we often blanket that metric as the quality of the model, which is something that I really am trying to emphasize for you guys to maybe avoid. And so this is actually a pretty famous example. Again, it's called the Anscombe Quartet, that was devised to kind of demonstrate this point. So these are 4 plots. Let me see if I can make this a little bit bigger. Okay, and so yeah, like, you know, when students see that this, like, yes, there is something very artificial in nature, and it is very constructed, right? But you know, this might be something that you were expecting to see, right? This is kind of the, like, randomly distributed data with your line fit through that point. But even like a cursory examination that goes beyond just the statistical significance in the R squared tells you a lot about the data. And so, you know, the first thing that I'll say is that, like, look at the data, right? And sort of see what that means. So in this case, model 2 was this one where you've got this nonlinear curve where you're fitting a line through it. This one is the same, where you actually have a sort of very linear set of data with what apparently is sort of a really large outlier along your sort of y-axis. And then here we have all this data with one sort of large outlier along your x-axis and actually also along your y-axis. And so, you know, this is like a nice little demonstration that that there are a whole lot of other things that we ought to think about besides your coefficients, statistical significance, and your R squared, that can tell you a lot about how good the model is and how well it sort of fits the data. Because I think, you know, from a purely mathematical standpoint, you know, these lines actually arguably fit the data in in the same sort of level of quality from some metrics as your first model. But I think that qualitatively, I could very easily argue that these lines don't do a really good job at fitting any of these data points. And so that'll be important to keep in mind going forward. Okay, sorry, I see a question that I didn't go over or kind of skipped over. Can you go over the meaning of the degree of significance again and how to interpret it? Yeah, certainly. So let's talk about this model. We estimate that the line is 0.5, has a slope of 0.5. Okay, and when it's statistically significant, it means that a certain percentage of the time, right? Like we know that this data is essentially exerting some kind of influence on the slope of your line. And it could be that as I change data, right? If I add another data point or I take one data point away, there's some influence on the sort of precision of our estimate of the slope. Okay. And so we want to, what the standard error does is it tries to accommodate the uncertainty about your prediction of what that slope is. And it could say, well, we think on average it's something like this, but sometimes it could be maybe a little bit less steep, and maybe sometimes it could be even more steep. And when you talk about statistical significance, all that's measuring is it's saying, well, how often is it that my slope is actually flat? And if the slope is flat, that just means that we don't think that my x values have any influence on my y, right? So if I were to draw a line like this, it just means when I go from one x value to another, my y values don't change. In other words, we don't think that x has a relationship with y. And so as I have this estimate for my line, it could be any number of different things, and sometimes it could even be this flat line. And if the occurrence of it being flat happens less than 10% of the time, we say it's statistically significant to the 0.1. If it happens less than 5% of the time, we say that it's statistically significant to the 0.05, and so on and so forth. So that is that's kind of the interpretation of statistical significance. It actually has a fairly deeper implication, though, which is pretty interesting. So there are thousands, hundreds of thousands, if not millions and millions of studies, just like data analysis based studies, right? Studies that do regression. And this ranges from everything from what we do, energy and transportation, all the way to, medicine, to physics, across basically all sorts of different studies. And if we imagine that the way in which they do it is the way in which we determine relationships between variables is through these regressions, where we say, X% of the time we are confident that it actually works, right? Because there's this demonstrable relationship between my X's and my Y's. There's also it also means, right, that that some percent of those times when we fit the data, it just happens to be that it's going to be like a zero effect. And so what that means is, if all of us are publishing studies where we say there's a statistically significant relationship at, say, the 5% level, then out of 100 studies, 5 of those studies on average will be having a false result, right? Like it means that 5% of the time there actually isn't a relationship. So that's something to think about, right? With these types of things, is that statistically it can't be that all of these studies that say, there's a relationship at the 5% level, that relationship actually exists. It actually means that 10 to 5 to 1% of studies out of all studies that do these kind of regression relationships are actually just wrong. So food for thought.
So in the given result that's on screen right now,
Yep.
we're saying that that X4 has has a chance of 0.2% of being just a horizontal line.
That is correct. That is
Okay.
exactly how you should interpret
Okay.
that. Yep.
Okay.
Yep.
Thank you.
Yep. Yeah, and don't forget that interpretation. Like, don't forget that is what that means, because we usually mean, I think statistical significance has really been like reinterpreted to kind of mean that that there is a real effect between my X and my Y, and that the model, and that particular model is better than other models that may demonstrate that there is no statistical significance. And again, I think as long as you keep in mind that exact interpretation, I think you're going to be safe. And it doesn't, right? And it doesn't tell you about what the data looks like. So again, I'll always make sure to if you're really trying to be robust with your work, like use all the metrics at your disposal to make sure what you're doing is correct and that the model fits, like makes sense, right? Like don't see this from your results and kind of pack it up, because you'll miss this bigger picture here. All righty. Okay, so in terms of the linear regression, I think that is all I'm going to cover today, but we actually can get to one other topic in R that I didn't quite get to last time, that I think will be sort of particularly helpful. So let's do that. So this is regarding a process called joins or merges. And so we kind of wrapped up last time with finishing about how to create data frames, which essentially are R's version of tables, and how to do filters. One of the other things that is particularly handful or useful, handy in data analysis is being able to manipulate tables so that you can merge them together. And so there are lots of examples of these. So for example, today, one I was working on is if you have like a survey data set and you have locations of respondents, and maybe you want to like merge that with census data, for example, because you know where they're living and you want to know the like characteristics of their surrounding areas. That's one example, one really simple example of a merge, right? Or if you're merging data sets about location attributes with like time attributes, if I have like attributes of a power plant that I then want to merge with, you know, how it operates over time. Another sort of common example. So this is a pretty sort of well-established procedure in computer science, and so we're gonna sort of cover that right now. Okay, so let's take a look at two hypothetical tables. So let's do table A, where I'll have X and Y, and my X is going to be A, B, C, D, and my Y is going to be 3, 4, 5, 6. And then table B is going to look like X and Z. So here I'm going to have C, D, E, F. Let me make this line a little shorter. And 7, 8, 9, 10. Okay, so I have this common column between these two called X, which I can use as the criteria for merging these two tables together. And you can actually merge them together in a couple different ways. If I think about a Venn diagram of my two tables, table A, table B, I can do a couple different procedures for my join. And so the one that you would kind of think of, I think the most intuitive one that folks often think of is this red area. And so this is going to be called an inner join. You can also have everything like this, and that is known as a left join in this case. And then you can have all of the data here, which would be a right join. And then you could also have all of the data, which would be something like this. And this is known as an outer join. So let's take a look at what all of these would look like. So my inner join is going to be, so we'll have X, Y, Z. So this is going to grab all of the points that overlap. Okay, and so that is going to be my C and D, right, are the only sets of points that exist in both sets of tables. And so in this case, we'll have C, D, my Y is going to be 5, 6, and my Z is going to be 7, 8. And so when you perform an inner join, this table is what's going to get returned back to you. Great. And then we've got a left join, X, Y, Z. Okay, and so in my left join, it's going to take everything from table A and then anything that overlaps with table B. Oops, I erased my C over here. All right. So it's going to be A, B, C, D. And then my Y is going to be 3, 4, 5, 6. And then, oops, I deleted that as well. Okay, so here we'll have a 7 and 8, right, as the part here. But then in my other points, it's going to be NA because there are no points that exist in that subset. So then you can imagine what the right join is going to look like, X, Y, Z. So it'll be C, D, E, F. Z is going to be 7, 8, 9, 10. And then we'll have 5 and, oops. We'll have 5 and 6 here, and then we'll have NA for my E and F. And then lastly, for my outer join, this will have all of the values. So this will be A, B, C, D, E, F. And here it will be 3, 4, 5, 6. And then NA, because those points don't exist. NA and Z for those points that don't exist. And then 7, 8, 9, 10. Okay. And so the type of merge or the type of join that you do kind of depends on what you're trying to accomplish, and whether or not you just want the complete data set of perfectly overlapping values. Oftentimes that'll be the case in regression type approaches for the columns that you care about because you need to have complete data, or you could do left join if you want everything in one data set, or an outer join if you need everything. And actually in my experience, again, it really depends on the context. I sort of commonly use all sort of three. So I say all three, even though there's four. The left join and the right join are essentially the same thing. It just depends on which one you're calling left and right. Okay. And let's show quickly how to implement this in R. So we'll jump back over here. Okay, so examples of joins / merges. So table A, I'm gonna have X. We'll just do the same thing. A, B, C, D, and then Y is gonna be, what did I have, 3 through 6. Table B will be thing where I have Z equals CD F, and then Y will be, or sorry, not Y, Z will be 7 to 10. So the inner join is going to be like this, merge equals, so table A, table B, and oh yeah, go ahead. Yep.
In table B in line 48, should that first thing be X instead of Z?
Oh, yep, you're right. Thank you. So we'll go ahead and run that. So we can see table A, table B, and then, so the by indicates which, the column name of the thing that you want to join on. So they don't actually have to be the same column. You could do, like if I called this column A, for example, you could do by X, by X equals that. Then by Y equals A. So you can reference columns of different names for the column that you want to overlap. Back. So let's see what that looks like. Great, so it's just, as I was saying, for the ones that overlap C and D. And then we can have a left join like this. So it's exactly the same, except at the end, we say all dot X equals true. So that means that you want everything in, you want to include everything in table A. And so now you'll see that we have included those ones. And you can imagine that the right join looks pretty similar, except instead of all X, we say all Y. And so now that will give you this table, right? 5, 7, 6, 8, and then NAs in here. And of course, the last one known as the outer join. And instead of saying all X or all Y, we just say all equals true. And that will give you the full sort of set. Yeah, okay. And so that is another sort of handy tool for combining data sets and tables together, especially to put them together for like one sort of cohesive set of analysis. Okay. And so that covers all the material that we were going to talk about today. So we'll end here. And again, as a reminder, so a couple administrative things. The first homework set should have been posted. So you should be able to see it on Canvas, and it will be due a week and a half from today. So next Wednesday at midnight will be the due date for problem set 1. And then there is going to be no class next or this Wednesday. I'm going to be getting my second shot, and I don't want to be like totally out of it when I lecture. So instead, I will post the lecture on Canvas alongside all the other lecture recordings. They'll be ready sometime late tomorrow night, and I will be recording it in the same way on Zoom. So if you feel like it, you are welcome to kind of join in, but it is definitely not required. It's not going to affect your participation either. So that will be tomorrow at 8 o'clock. Yeah, tomorrow at 8 o'clock at night, and it's going to be on the same channel. So anyone who wants to come live, you know, you can still sort of participate like a regular class. Otherwise, yeah, just watch the lecture, and apologies for the inconvenience. Okay, and so I'll stick around for a couple of minutes in case anyone has any questions. Otherwise, I will see you either tomorrow night or next Monday.